The purpose of this video lecture is to inform you guys about the factors that shape global climate. We're going to start by asking the question, why focus on climate? How does it relate to plant growth? Next, I'm going to run through some of the factors that shape global climate, everything from the shape of the earth to things like topography. Then finally, we'll take a look at climographs and talk about the things that one can learn from studying a climograph. So before we get started, I want to make sure everybody understands the difference between climate and weather. Climate is a long-term regional trend in temperature and precipitation, whereas weather is a short-term local trend in temperature and precipitation. So for example, if I were to say in Northern California, we generally have cool, moist winters and warm, dry summers, that would be a statement about the climate. It's regional, and we're also talking about long-term patterns of temperature and precipitation. However, if I said, today in Mount Shasta, it's 60 degrees with clear skies, that would be a statement about the weather. It's short-term, it's more localized, it's a more localized description of the temperature and precipitation. Okay. So make sure you know the difference between these two terms, climate and weather. We're talking about climate in this week's module, so long-term regional trends in temperature and precipitation. Next, I want to make the point that climate matters to plants. So both moisture and temperature have a huge impact on whether a plant can survive in a particular region. And the example that I have for you on this slide relates to the plant hardiness zone. So the USDA will label seeds that you buy with one of these codes, 5A to 10B. There's other codes out there, but these are the ones that we have in our region in Northern California. What these codes denote is the average annual extreme minimum temperature. So how cold it gets on the really cold days in the winter for that particular region. So you can see we do have some of these colder zones, like at high elevation on Mount Shasta. Down towards Redding, they have some of these more moderate zones, 9A, 9B. It doesn't get as cold there in the winter. So when you're at the nursery and you're buying seeds to plant in Mount Shasta City, you're going to want to buy ones that have these lower codes, 6A, 5B. Plants that have the higher numbers, 10A, 10B, they're probably not going to be able to tolerate the cold temperatures in the winter, and they're not going to be able to overwinter in these colder regions of Northern California. So, moisture and in this case temperature do have an impact on whether a plant can survive in a given region. More than survival, moisture and temperature just have a huge impact on how much a plant or a plant community or an entire ecosystem is going to grow. These two graphs show us dry matter production of plants, so how much biomass was out there generated by plants. And this one on the left has mean annual temperature in degrees Celsius on the x-axis, whereas the one on the right has mean annual precipitation in millimeters on the x-axis. As you can see, when it gets warmer and when there's more moisture, there's more growth in a plant community. So moisture and temperature, whether we're talking about these extreme winter temperatures or in general looking at the temperature and the amount of moisture, we see that they have an impact on plant growth, and they have a huge impact on which communities we find growing in our region. Okay, so we're going to take a couple steps back to the global scale and start talking about the factors that shape climate. The first one we're going to look at is the tilt and rotation of the Earth, which causes seasons. So on this diagram, we've got the sun, and then we've got the earth, and it's showing the earth revolving around the sun. So here, it's over here to the right of the earth, or I'm sorry, it's over here to the right of the sun. Here it's to the left. Here it's behind the sun. Here it's to the left, and then here it's in front of the sun. So the earth revolves around the sun, and as it does that each year, so that takes a year, we experience different seasons in different places on the planet. So here we see in this particular arrangement, the southern hemisphere is facing the sun. So that would be summer in the southern hemisphere. In this particular conformation, the northern hemisphere is facing the sun. So that would be summer in the northern hemisphere. When it's summer in the southern hemisphere, it's going to be winter in the northern hemisphere. We're not receiving as strong of energy, as much energy from the sun. And that's why we have colder temperatures in the winter. And the point here where the earth is shown behind the sun and in front of the sun, those would be the other seasons. This one would be fall and spring in the southern and northern hemisphere. And this would be spring and fall in the southern and northern hemisphere respectively. So it's this tilt of the earth on its axis and its rotation around the sun that causes these seasonal differences in temperature on an annual basis. The next point I want to make is that regardless of the season, in general, there's more energy coming from the sun that's landing near the equator of our planet than is landing on the surface of the planet near the poles. So here we see these three arrows down here, B, and these three arrows up here denoted by the letter A. And if you take a look at the Earth, you see that this same amount of solar radiation is diffusing over a smaller area in the tropics. So those solar rays are hitting the planet at a more direct angle close to the equator. Whereas up here, because of the shape of the Earth, the same amount of solar energy is being spread across a larger area of the Earth's surface. So that means at any given point in this circle, there's going to be less energy that plants use to grow. Whereas over here, in any given point in this circle, there's going to be more solar energy, this energy that's so important to allowing plants to photosynthesize and grow. So this results in over twice as much heat and solar energy being delivered to the land area at low latitudes on our planet compared to at the poles. So we've got seasonal differences in temperature, and we also have huge differences in the amount of heat and solar energy that's being delivered to the globe based on the position of the particular location. It's going to be a lot more concentrated. That energy and heat is going to be a lot more concentrated at low latitudes. And we can see that uneven heating when we look at this figure. So this figure shows us temperature here denoted by color. So the really cold areas are in these cool colors, purple, and then the blues, and then the warmer areas with higher average annual temperatures are being shown here in the warmer colors, all the way up to this red color. So you can see what we just looked at on the previous slide. In general, that the fact that there's more heat and solar energy being delivered to the low latitudes near the equator means that it's hotter there. So we see hotter temperatures near the equator, and they get colder as we move away from the equator to the north and the south pole. So uneven heating which was explained on the previous slide, leads to temperature disparities by latitude that we can see here in this figure. Okay, so we know that temperature is really important in determining which plants are going to grow where. So is moisture. And moisture is also going to vary based on where you are on the planet. So one reason why moisture varies on our globe is something called air mass circulation. So we just learned that the warmest part of our planet is going to be, in general, around the equator. So the air in the atmosphere in the equator is going to be warmer than other places on Earth. That warm air is going to hold a lot of moisture. Warm air picks up moisture from water bodies, and it has a greater ability to hold that moisture than cool air. You probably also know that warm air rises. So if you heat your house with a wood stove, you've probably experienced this where, you know, the upstairs of your house is getting really warm, but the downstairs is staying cold. That's because the air that you're heating up is less dense and it rises. So in the tropics, we have moist, warm air masses that are rising. As they get farther apart, or as they get farther away from the Earth's surface, it's going to get colder up there in the upper parts of the lower atmosphere. And as they cool, they're going to lose their ability to hold some of that moisture, and it's going to fall down as rain. So this is showing us these air masses rising. So that's what this part of the arrow is showing us. And then down here, if we look at this figure, it's showing us annual precipitation in inches by latitude, and we can see that it's highest. Because of this atmospheric air mass circulation, it's highest at the lowest latitudes, right by the equator. If we take a look, after these air masses rise, they're either going to head north or they're going to head south, and they're going to continue to cool down because they're still far away from the surface of the planet, which is warmer. As they cool down, they're going to become more dense again, and they're going to drop. So that's why we see this air mass circulation cell showing air rising and then dropping. And this one as well. The air mass was rising when it was warmed, and then it's dropping as it cools. It's already dropped its water in the tropics as it started to cool. So now we have a cold, dry air mass descending on the surface of our planet at around 30 degrees north and south latitude. This air, this dry, cold air, is not going to bring a lot of rain. In some cases, it actually picks up moisture from the land. And if we take a look at this graph down here, right around the 30s, we see relatively low amounts of annual precipitation. This is where a lot of the deserts on the planet form, like this great African desert, the Sahara. If we take a look at this next air mass circulation cell, the air is going to get warmed again, and it's going to rise again, actually up here. So here we have air masses descending at the 30s. We're going to have air masses rising again at 60 degrees north and 60 degrees south latitude. The air is going to get warmed as it's near the surface of the planet. And that's what's causing these little increases, these slight increases in precipitation in those temperate regions of the planet. So again, we've got warm air, so it's going to be able to hold a lot of moisture, certainly not as much as the air close to the equator, but a little bit of moisture. As it rises, because it's been heated up on the surface of the planet, it's going to drop some of that precipitation. So that's what we see in this bottom graph, around 60 degrees south and around 60 degrees north latitude, a little bit more rain. That's in our temperate regions of the planet, the temperate and boreal regions of the planet. So I want you to know that there's huge variations in both temperature and precipitation on the planet, and one of the reasons we see the variation in precipitation is the circulation of these air masses, which relates to the uneven heating of our globe. Other factors have a big impact on climate, and one of them is the distance from a large body of water like the Pacific Ocean. In this case, I've compared the temperature in Astoria versus Pendleton, Oregon. Astoria is less than 1 mile from the ocean. Pendleton's 250 miles from the ocean. It's this red mark right here. So on the next line in this table, we see the average temperature in January. We see that it's going to be a little bit warmer in Astoria. It's going to be a little bit colder in Pendleton. The ocean, all that water in the ocean is relatively warm, and it helps to warm up the land during the winter. In Pendleton, they're really far from the Pacific Ocean, so they don't have the warming effect of the water. Likewise, in the summer months, we'll see that the ocean is going to be relatively cold compared to the air, and it's going to cool things down in Astoria compared to the temperatures that they would experience inland, where they're farther away from the ocean in Pendleton. So put it all together and you see that there's going to be a reduced temperature range in Astoria. The Pacific Ocean is cooling it down in the summer, and it's warming it up in the winter. We see more extreme changes in temperature on an annual basis further inland. So proximity to these huge bodies of water will also have an impact on local climate. And so does topography. Topography affects the wind patterns. So in this diagram, we see air coming off of the ocean, so it's going to be relatively warm if it's coming off the ocean in the winter, because the ocean's going to be warmer than the land. So we see that air mass traveling over the ocean and then cooling down as it reaches the land. It's going to cool down even further if it travels up in elevation because of a mountain range. We just talked about, when we were talking about air mass circulation, that warm air masses can hold more moisture than cold air masses. So we're going to see the same thing happening. As this air mass is forced to rise, this is called orographic lift, it's going to cool down. With a drop of temperature of 20 degrees Fahrenheit, the water content in the air is going to decrease by half. That means it's going to rain over here on this side of the mountain range. Then what we're going to have is a cold, dry air mass over the ridges, over the top. They're going to descend on the other side of this mountain. They're going to go down in elevation. That air mass is going to warm up, and it's not going to be bringing rain over there. In fact, if it's really dry and it gets really warm, it might even start taking moisture out of the soils on the leeward side of the mountain. This is called the rain shadow effect. So we would say that this area was in the rain shadow of this particular mountain range. So, the seasons, the latitude, air mass circulation, proximity to a large body of water, and the topography have a huge impact on both temperature and precipitation. Okay, one last point I want to make is that we can display climate data in a graph called a climograph. So here I have two climographs, one for Banda Aceh, Indonesia, and one for Cairo, Egypt. It's showing both temperature and precipitation. It's showing temperature in this light blue line that's probably a little bit hard to see, and it's showing precipitation in millimeters in this darker blue line. So right away, we can get a lot of information about the climate of these two areas. What I see is extremely consistent temperatures, relatively high, and consistent temperatures in Banda Aceh. Looks like it's always 75 or 80 degrees. At low latitude, the seasons don't have as big of impact. The amount of solar radiation doesn't change that much at those low latitudes, so we would expect the temperature to stay the same. The other thing that I see here is really high amounts of precipitation, up to 200 millimeters a month in the month of December, which is what we would expect to see. This is really low latitude, and we talked about how at those latitudes where you have warm air masses rising, you're going to see a lot of precipitation. That's in contrast with what we see in Cairo, where there's almost no precipitation at any time in the year. Notice the latitude. So this is, Cairo is in the area on the globe where we have dry air masses descending and there's very little rainfall. We do see a little more variation, a little more seasonality in the temperatures in this particular region. So these are two really different regions climatically. I would expect there to be very different plant communities in these areas. Some kind of tropical forest would be supported by a climate like this, and a desert or desert vegetation would be supported in a climate like this. Temperature and precipitation have a huge impact on plant growth. And this graph just kind of illustrates that. It shows the distribution of biomes globally, where a biome is a major regional biological community, such as a desert or a forest. And you can see tropical forests at low latitudes. You can see tundra up at high latitudes. You're going to explore these biomes more in one of the other readings that you do for this week. Okay, so the take-home message is that climate varies a lot in different places on our planet. You should know what climate is and how it differs from weather. You should know why plants are sensitive to climate. They need water, they need warmth in order to grow. You should know how to read and interpret a climograph like the ones that we just looked at. And you should know how the following factors shape global climate: the tilt and revolution of the Earth around the sun, uneven heating around the globe, the air mass circulation and how it relates to the amount of precipitation we expect in a given area, proximity to a large body of water, and orographic uplift due to topography and the rain shadow effect. You should also be familiar with the term biome.